The title of the lesson was called Power Series. Power series have a very specific form that looks like this. Sigma n equals 0 to infinity. It doesn't have to be 0, but just in general. A sub n times x to the n power. It's called a power series because x just has increasing powers as you go. So a0, a1, x to the first, a2, x squared. So if you notice, Taylor-Maclaurin series are just a very specific form of power series, except for in the particular case of Taylor-Maclaurin series, the coefficients in front of the x's are determined by the nth derivative at 0 for Maclaurin over n factorial. Okay, but they're a much more general form. But let's take a look at something that occurs, and we'll look specifically at ln of 1 minus x, which you should have done in the worksheet. So I'm going to increase the number of terms, and I want you to watch notice what happens to the approximation as I increase it up to 20 terms. Okay, you notice that it's pretty good in this region, but beyond that, it's no good at all. So if I wanted to examine a point here, the Maclaurin series for ln of 1 minus x is actually no good. Our first example will be the function ln of 1 minus x, which in sigma form, which we found earlier, actually started at 1. There's a negative, and then it just went 1 over x, or 1 over n, x to the n. So notice, again, a sub n is determined as 1 over n, which is related to this jobby. Okay, so in any case, what I want you to notice is that this only converges in a certain interval. Okay, so look at it again. It only converges, it seems like from here to here, but anything outside of that interval is no good. We're going to call that the interval of convergence. So what we want to do is we want to find the interval of convergence. Okay, so how do we do that? There's going to be 3 steps that we're going to take. Step 1 is we're going to use a test. And it's going to usually be one of 2, root or ratio. The reason for ratio is, if you remember sine and cosine, their Maclaurin series have the factorial, okay? But usually we'll try root. Since there's no factorial here, I'm just going to use root. And because root test has absolute value, I'm going to ignore this negative out front. So I'm just going to view it like this, x to the n over n to the 1 over n power to the nth root. Now what we want this jobby to do is to converge. If you remember from root test, in order to force something to converge, I want that jobby to be less than 1. Okay, so we would like this to be less than 1. Okay, so let's simplify a little bit. What I'm going to get is I'm going to get limit as n approaches infinity, x over n to the 1 over n, and I want to force this row to be less than 1. Keep in mind that limit from before was just 1, so we worked it out. So all we really have left is absolute value of x has to be less than 1. Okay, well, what values of x satisfy that result? So for step 2, we're going to solve for x. Okay, let's solve for x. Absolute value can just be broken up into 2 cases. Take the case where the absolute value is gone, and that's the positive case, and then there's also a negative case, and we flip the inequality. So in the number line, what we're saying is this power series, or Maclaurin series, only converges between -1 and 1. And you can check here, between -1 and 1, it seems to be good. However, keep in mind that when it's equal to 1, it's inconclusive for the root and ratio test. So we actually don't know what happens at the endpoints. We just know that it converges everywhere in between. So the third thing we need to do is we need to test the endpoints. Okay, so how do we do that? So our left endpoint is -1. Okay, so don't forget your sigma. I'm going to ignore the negative in front of the sigma because it's not going to affect convergence or divergence. The sigma was this jobby, 1 over n x to the n power, 1 over n x to the n power. So I'll rewrite it, 1 over n x to the n, but x is now going to be -1. Okay, if you look at this is an alternating series. It'll pass gate number 1 because the terms go to 0, and it gets smaller. It's actually the alternating harmonic, so this actually will converge by alternating. We don't need to show that work. So at -1, I'm going to put a closed bracket. Okay. Now if I test 1, I'm going to get sigma n equals 1 to infinity, 1 over n, 1 to the n, right? And if you look at it, it's just really the harmonic series, because that 1 to the n doesn't matter, and we know this is divergent by p series. So what we're saying is it's an open bracket here. Okay, so the final answer is that this function only converges from -1 to 1, closed at -1, open at 1. And you can check here, at 1 there's actually an asymptote, which is why it can't converge. And if I do take more and more terms at -1, it'll actually match the function exactly.